Good afternoon, everybody. I'm Anjana Joshi. Today we shall be talking about Z transforms, Unit 5, continuation with the calculus of variation. To start with, let us understand why Z transform is necessary. Basically, in the previous semesters, you people have studied about what Laplace transform is about and the Fourier transforms. You could realize that the Laplace transforms and the Fourier transforms were actually acting on the functions which had continuous arguments. But Z transforms acts on the function which have the arguments in terms of discrete integer values. And the application of Z transforms can be seen in signals in systems. That is, Z transforms basically converts the discrete time domain system to complex frequency domain system, and it is also used for determining the difference equation. Now we could see that the Laplace transforms were basically used in terms of continuous arguments, and Z transforms are used for discrete valued integer functions. So let me start off with the definition of Z transforms. Please make a note that here the Z transforms are acting on discrete valued integers. So keeping that in mind, let us define what Z transform is and how it is denoted. Also, we shall discuss about the inverse Z transforms. So to start off with the definition of the Z transforms, you can say that if I have a function that is for Z transforms, to start off with the definition, I can say if un is equal to a function of n, where n takes the value as 0, 1, 2, 3, so on, and un will be equal to 0 for n less than 0, then Z transform is denoted by Zt of un, which is equal to summation of un z raised to minus n, and take a note that n takes the values between 0 to infinity. Now you can see that this will be nothing but a function of z, that is, I can write it as u bar of z. That is, I had a function in terms of n, which is now converted in terms of a function of z when we have applied Z transform on the function of n. And also the inverse Z transform can be written as inverse Z transform of u bar of z will be equal to un. That is a function of n. So this is the basic definition of the Z transforms, how it is denoted and how it is defined. Also, we have talked about how the inverse Z transform can be written. With this definition, we shall now talk about few of the Z transforms for a few of standard functions. So let us start off with the first standard function which is necessary for us. So first thing we are starting is Z transform of some standard functions. So let us go for a very important function of n, that is, we are supposed to find Z transform of k raised to n. Now let us make use of the basic definition of the Z transform. We very well know that Z transform of un is given by summation of un z raised to minus n, n ranges between the value 0 to infinity, discrete values. So if I want z transform of kn, I can write this as summation of un, that is the function of n here is k raised to n into z raised to minus n, and n is taking the value 0, 1, 2, 3, so on. And this can be furthermore written as summation k by z by k whole raised to minus n, n taking the value from 0 to infinity. Now if I can just write this in a series, I can write this as, first of all, n is taking the value as 0. So let me make a change here. That is, I shall have this as z by k whole raised to plus n. So this will be z transform of k raised to n is equal to, let us give the values of n as 0, 1, 2, 3, etc. So if I can give the value of n as 0, I'll get this as k by z whole raised to 0, which is nothing but 1, plus the next value I can take for n is 1, because discrete values is what we are discussing. So we shall get this as k by z whole raised to 1 plus the value of n is 2 here, k by z whole raised to 2 plus so on. Now if you can just look onto this series here, you can see that this is something of the form 1 plus r square plus r cube. If you can look onto this, you remember that in your plus 2 you people had studied something about the geometric series. Yes, this is taking the form of the geometric series, and you can see that the sum is towards infinity. Sum is towards infinity, and we very well remember that the sum of the geometric series, okay, is given by 1 minus r, r being the common ratio. So making use of this concept, I'll just write it down. What I meant to say is, that is, this is a geometric series. This is a geometric series of the form 1 plus r square plus r cube plus so on, whose sum to infinity is given by 1 by 1 minus r. Here you can see that the common ratio r is nothing but k by z. So making use of this geometric series, sum to infinity, I can write the z transform of k raised to n is equal to 1 by 1 minus r. R obviously is taking the value of k by z. So this will be 1 by 1 minus k by z. So if I can simplify this further, this will be 1 by z minus k divided by z. Obviously, this can furthermore be written as z by z minus k. Therefore, you can say that the z transform of k raised to n is given by z minus k. This is the z transform of the function k raised to n. I shall go through this again. What we have got is a function of k raised to n, and we have gone for the basic definition of the z transforms, which is given by un z raised to minus n, summation ranging from 0 to infinity. And then since we are talking about k raised to n, I can just take this function of n as k raised to n, z raised to minus n. This further can be written as k by z whole raised to n, because we very well know that z raised to minus n is nothing but 1 by z raised to n. That is what is being used here, and then we just go on giving the values of n, discrete values, starting from n is equal to 0. So k by z whole raised to 0 is 1, k by z raised to 1, and then k by z whole raised to 2, so on. So you can see that this is forming a geometric series which is of the form 1 plus r square so on, whose sum to the infinity is given by 1 minus r. This concept is studied by you in +2. And then if you can just compare this, you can see that the r value is nothing but k by z. So I shall replace this r by k by z here, do the simplification, and I shall obtain the z transform of k raised to n to be equal to z by z minus k. This is the z transform for the function k raised to n. Now let us go for a very particular case of what can be the z transform of 1. The second one what we shall be discussing will be a particular case of the z transform of k raised to n. Second thing we are discussing is z transform of 1. Now, just now we have found out that z transform of k raised to n is nothing but z by z minus k. Now, I want z transform of 1. So, what I simply do is put k is equal to 1. So if I can just take k is equal to 1 here, I shall have 1 raised to n, and n is taking the discrete values from 0 to infinity. Hence, I shall have this as z transform of 1 is equal to z by z minus 1. So we have got the second result, that is z transform of 1 is nothing but z by z minus 1. We have taken that the z transform of 1 can be obtained as a particular case by making use of z transform of k raised to n. I have simply replaced k as 1 and then I have got the result for z transform of 1, which is z by z minus 1. And now let us go for next standard function and how it is applicable when we are supposed to find out what can be the z transform of n, n square, n cube, so on. So let me go for one of the results. So let us take the next one. The third one is z transform of n raised to k is given by minus z d by dz of z transform of n raised to k minus 1, where k is an integer, right? So in particular k is a positive integer. Now to solve this, let me make use of the left hand side first. That is, I have got the left hand side to be equal to minus z d by dz of z transform of n raised to k minus 1. Now, this can be written as minus z d by dz also, since z transform of un is nothing but summation un z raised to minus n ranging from 0 to infinity. By using this definition, I can write this as summation n is equal to 0 to infinity un taking the value of n raised to k minus 1 z raised to minus n. I have just taken it in terms of the definition of z transforms. So this can be minus z. Now I can differentiate this term here by the rule of the differential signs. So I can write this as summation n is equal to 0 to infinity, and now you can see that the differentiation is with respect to z. So this will be n raised to k minus 1 into differentiation of z raised to minus n with respect to z will be minus n into z raised to minus n minus 1. I am repeating. Here we have got it from the definition of z transform, that is summation of n raised to k minus 1 z raised to minus 1, and the differentiation is with respect to z. Hence this summation n is equal to 0 to infinity. I shall keep n raised to k minus 1, and since the differentiation with respect to z, we know that differentiation of z raised to minus n with respect to z will be minus n into z raised to minus n minus 1. So if I can simplify this further, this can be written as, since the summation is on n only, I can write this as summation n is equal to 0 to infinity. You can see that I have a minus over here and a minus over here. The product of these two minus is a plus. So hence we shall have this as n raised to k minus 1 into n into z raised to minus n minus 1 into z. So this will be summation n is equal to 0 to infinity, and if I can go further with this, n into n raised to k minus 1. By theory of indices, I can write this as n raised to k, and this will be z raised to minus n minus 1 plus 1. So this is n raised to k into z raised to minus n. But what is this basically? This is nothing but z transform of the function n raised to k. Now if you can see, this is nothing but the RHS. So we have got that this is nothing but RHS. Hence, we have proved that the z transform of n raised to k, which is equal to minus z, d by dz of z transform of n raised to minus k, can be obtained by making use of these concepts here. Please make a note that the differentiation here is with respect to z. So differentiate z raised to minus n with respect to z and simplify this by using the theory of indices, and this is the result what we are going to get. And this is the result we shall be making use of to find out what can be or what is the z transform of n square, n cube. Simple thing, what we do is we just replace the values of k as 1, 2, 3, etc. So if I can replace k value as 1, I shall be getting the z transform of 1. If I replace k as 2, I shall be getting the z transform of the function n square, and so on. So let us start finding what is the z transform of n. Yes. So let's go for the next function, that is z transform of n. Now, to find this out, let me make use of the result which we have just found out. That is, we know that z transform of n raised to k is nothing but summation of, minus z d by dz of z transform of n raised to k minus 1, where k is a positive integer. Now, I have to obtain the value of z transform of n. So you can see that I can just take k value as 1. If I can take k value as 1, I shall get this as z transform of n is equal to minus z d by dz of, that is differentiation with respect to z, on z transform of, since k value is 1, if I take k as 1, 1 minus 1 is 0, so n raised to 0 is 1. Have I made that clear? We have got z transform of n raised to k minus 1. Since I want the value of z transform of n only, k will be taking the value as 1. So if I can replace the k value as 1 here, you can see that this will be n raised to 0. Obviously, n raised to 0 will be taking the value of 1. And we have already found out the z transform of 1, and the z transform of 1 is given by z minus 1. We have already studied about how we had obtained z transform of 1, which is z by z minus 1. Now, the next step is just to differentiate this with respect to z by making use of the quotient rule. So, we shall go for z transform of n. Z transform of n will be equal to minus z. Go for the quotient rule. We shall get this as z minus 1, and differentiation of z is 1, minus z, again differentiation of z minus 1 with respect to z is 1, divided by z minus 1 the whole square. Now if I can simplify this, this will be minus z, z minus 1 into 1 is z minus 1, minus z plus 1 is minus z, divided by z minus 1 the whole square. So you can see that the plus z here and the minus z cancel each other. So we have minus into minus plus z divided by z minus 1 the whole square. This is how we find out the z transform of n. So here I shall repeat, this is the result which we had got previously, which says z transform of n raised to k is minus z, d by dz of z transform of n raised to k minus 1. Now if I have to obtain the result for n, you can replace your k value as 1 or take k as 1. So if I can take k value as 1, you can see that this will be n, k is taken as 1, 1 minus 1 is 0, so n raised to 0 is 1, and then I have made use of the result of z transform of 1 is z by z minus 1, and then have differentiated by making use of the quotient rule. I have just simplified, and this is what we have got the result for z transform of n, which is z by z minus 1 the whole square. In the similar fashion, we can find out what can be or what is the z transform of n square. So we shall be making use of the same result, that is z transform of n square. So we go for the same result which we had obtained, that is z transform of n square or n raised to k is given by minus z d by dz of z transform of n raised to k minus 1. So here if you can see, I require n square, so I can just take the value of k to be equal to 2. So I can write this as z transform of n square. Remember, k is taking the value 2, so this is minus z d by dz of z transform of n raised to k. K is taking the value 2, so n raised to 2 minus 1 is n raised to 1, which is n. So we have minus z d by dz of z transform of n. So this will be equal to minus z d by dz of the z transform of n. We have just obtained that the z transform of 1 is given by z minus 1 the whole square. So z by z minus 1 the whole square. So the next step is to differentiate z by z minus 1 the whole square with respect to z. So this will be equal to minus z. Use the quotient rule again. So you shall have this as z minus 1 the whole square into differentiation of z is 1 minus z. Differentiation of z minus 1 the whole square will be 2 into z minus 1, and differentiation of z with respect to z is 1 divided by z minus 1 whole raised to 4. We have just made use of the quotient rule. So to continue with this, we shall have z transform of n square will be equal to, I'll simplify, minus z. You can see that z minus 1 the whole square is in this term and z minus 1 over here. So we can take z minus 1 common. So if I can take z minus 1 common, I shall be left with z minus 1, because here there is a z minus 1 whole square, one is taken as common, and the other one is left as minus 2z divided by z minus 1 whole raised to 4. I am repeating again, out of these two, z minus 1 is taken common, so I shall be left with 1 z minus 1 over here and minus 2z here divided by z minus 1 whole raised to 4. So this is minus z. If I can simplify, I have a z minus 1 over in the numerator and z minus 1 raised to 4 in the denominator. So if I can cancel up, I will be left with z minus 1 minus 2z divided by z minus 1 whole raised to 3. Z minus 1 here, one of z minus 1 here gets cancelled. So here we shall be left with minus z. Z minus 2z will be minus z minus 1 divided by z minus 1 the whole cube. So if I can simplify this further, minus z into minus z will be a plus z square, minus z into minus 1 will be a plus z divided by z minus 1 the whole cube. So this is how we have obtained the z transform of the function n square. in the similar fashion, you people can find out what can be the Z transform of n cube, n raised to 4, etc. Now, let us talk about one of the important properties of the Z transforms. As we had already discussed about the Laplace transforms, the properties which hold good for the Laplace transforms usually hold good for the Z transforms also in terms of discrete valued integers. So if you remember, you have studied about the linearity property in the Laplace equation. Similarly, here the Z transform also holds good for the linearity property. So what linearity property for the Z transform is? It is given by the statement if linearity property statement, linearity property. So this property states that if Un and Vn are any two discrete valued functions, then Z transform of C1 Un plus C2 Vn can be written as C1 Z transform of Un plus C2 Z transform of Vn, where here C1 and C2 are the constants. Right? So the Z transform of C1 Un plus C2 Vn can be written as C1 Z transform of the function Un plus C2 Z transform of the function Vn. Note that here C1 and C2 are the constants. This is the linearity property related to Z transform. Now let us go for one of the rule named as the damping rule. Again, very important rule in terms of signals and systems. So let us talk about the damping rule. Yes. Now, what damping rule basically states is, damping rule, it states as if Z transform of Un is equal to U bar of Z, if Z transform of Un is equal to U bar of Z, then Z transform of, first one, Z transform of A raised to n Un is given by U bar of Z by A, and second, Z transform of A raised to minus n Un is given by U bar of Az. These are the two rules which comes under the damping. Now, this damping rule we shall be using to find out what can be the Z transform of hyperbolic functions, say cos hyperbolic and the sine hyperbolic. So let me prove this damping rule. Now the proof here behind this is very simple. We shall be making use of the basic definition of the Z transforms. So to start with, you can say that we know Z transform of Un is given by summation Un Z raised to minus n ranging from the range 0 to infinity. Now we have this to be defined as U bar of Z, a function U bar of Z. Now let us go for Z transform of A raised to n Un. So I shall be having this summation n is equal to 0 to infinity. Here I can write it as an un z raised to minus n. So this can be furthermore written as summation n ranging from 0 to infinity, discrete values of course, un z by a whole raised to minus n. That is, we know a raised to n can be written as 1 by a raised to minus n. This is what I have used here. Now if you can just look onto this, whenever we have summation on un z raised to minus n, I have got it as a function of z. Here I have got it as z by a whole raised to minus n. Then obviously I shall be having this to be a function of z by a. This is how we have got the z transform of a raised to n un to be equal to u bar of z by a. That is, whenever we associate a raised to n, here in particular, to a function of n, the result what we get after going for the z transform on it is we shall be having a function of z by a. A very important result in terms of your signals and systems topic. And then let us go for the second one, that is now we are supposed to obtain z transform of a raised to minus n un. The proof is very much similar to the previous one. That is, we shall have this as summation. That is, you can say we know that z transform of un is equal to summation n ranging from 0 to infinity un z raised to minus n. So this will be equal to summation n ranging from 0 to infinity, because now we are finding the z transform on a raised to minus n un. I shall have this function here as a raised to minus n un z raised to minus n. So furthermore, this will be summation n is equal to 0 to infinity un, and this is a raised to minus n into z raised to minus n, which will be equal to summation n ranging from 0 to infinity un a into z whole raised to minus n. In the similar fashion, as I told you, this is nothing but u bar of z. I have got z raised to minus n. Here we have got as a z raised to minus n. So this will be u bar of a into z. This is what we have got. Z transform of a raised to minus n un will be u bar of a z. This completes the damping rule proof. Now let us find out what happens when we make use of this rule for few of the standard functions whatever we had discussed. That is, so if I can just give examples on damping rule. If I can go for the examples on damping rule, that is, if at all I have to find z transform of k raised to n into n. Yes. So basically, see, this is something of the form z transform of a raised to n into n. What we do, we will have z transform of n. Just now we have talked about z transform of n, and z transform of n is given by z minus 1 the whole square. Now this is what we have dealt already. Now if I want z transform of k raised to n into n, that is k raised to n acting on n, by making use of the damping rule, here you can see that whenever a raised to n gets associated with un, your z is replaced by z by a. So here your z will be replaced by z by k. That is, instead of a, Here we have it in terms of k. So let me replace all z's by z by k, and this will be z by k minus 1 the whole square. I am repeating again, I am making use of the damping rule here. If you can just see, what I did here is I went for the z transform of n, and we very well know that the z transform of n is given by z minus 1 the whole square. So whenever k raised to n gets associated with it, your z will be replaced as z by k. Here also this z is getting replaced by z by k. This is basically because of the damping rule which we have just studied. Now the next thing is to just simplify this further. That is, I shall have this as z transform of k raised to n into n to be equal to z by k whole divided by, if I can take the LCM and simplify this, this is k minus 1, k minus k by k the whole square, or further this is z by k into k square divided by z minus k the whole square. So furthermore, you can see this, one of the k's are getting cancelled. So we shall be left with kz by z minus k the whole square. This is what we have as z transform of k raised to n into n. You can see the effect of damping on the function n. So in the similar fashion, we shall find out what can be the z transform of k raised to n into n square. K raised to n into n cube and k raised to n into n raised to 4, etc. can be done by yourself. So I'll go for the second example, z transform of k raised to n into n square. So again we are supposed to make use of the damping rule, but we very well know that the z transform of n square is given by z square plus z divided by z minus 1 the whole cube. So if I associate k raised to n with this n square, all your z's will be replaced by z by k because of the damping rule. So this becomes z by k the whole square plus z by k divided by z by k minus 1 the whole cube. The further things are just a simplification. These two examples are done for you to understand the importance of the damping rule. So if you can simplify this further, you can see that here I shall have this as z square plus kz divided by k cube divided by, we shall have this as z minus k the whole cube divided by k cube. So yeah, this will be k square, right? So this will be z square plus kz by k square into k cube divided by z minus k the whole cube. So further simplification will give you z square plus kz times k divided by z minus k the whole cube. So further simplification will give you k z square plus k square z divided by z minus k the whole cube. So this is for you to understand the importance of damping rule. The simplification can be done by yourself. Now, as I've told you, you can similarly find out what can be the z transform of k raised to n into n cube, k raised to n into n raised to 4, etc. Now, what can be the z transform of k raised to minus n into n? All this while we were discussing about what happens when k raised to n is damped on n or n square. Now, if we have k raised to minus n associated, the fashion of solving it is similar, by making use of the damping rule, that is Z transform of n is given by Z minus 1 the whole square, and then if I can go for Z transform of k raised to minus n into n by making use of the damping rule, you can see that your Z is now replaced as Z into k. So if you have k raised to plus n, you have seen that Z's are all replaced by Z by k. Now if your n's has multiplication here, so with damped with k raised to minus n, all your Z's are replaced by Zk. So this is Zk minus 1 the whole square. So these are few examples on how damping rules are used. So now let us go for one more important transformation, that is how Z transformations are obtained for cos theta, that is the trigonometric functions, the cos n theta and the sin n theta. There are many ways of solving it. Let me go for one particular way wherein I'll be making use of e raised to in theta. So we are supposed to find out what can be the Z transform of cos n theta and Z transform of sin n theta. So we have studied in your previous classes that e raised to in theta is nothing but cos n theta plus I sin n theta. So I shall be making use of this concept. So to obtain the Z transform of cos n theta and sin n theta, if I take Z transform of this, that is Z transform of e raised to in theta, I'll be getting this as Z transform of cos n theta plus I sin n theta. So furthermore, this is nothing but Z transform of e raised to I theta raised to n is equal to Z transform of cos n theta plus I Z transform of sin n theta. See, if you can observe it, we have made use of the linearity property here. That is, if I can obtain what is the Z transform of e raised to I theta raised to n, I shall be obtaining what can be the Z transform of cos n theta and sin n theta. So now let me just concentrate on Z transform of e raised to I theta raised to n. Now this, if you remember, we have just found out Z transform of k raised to n is nothing but Z by Z minus k. So here I have e raised to I theta in terms of k. So I write this as Z by Z minus e raised to I theta. That is k here is just replaced by e raised to I theta. Now this I shall just write it as Z minus e raised to I theta into, I shall multiply and divide by Z minus e raised to minus I theta divided by Z minus e raised to minus I theta. I have just multiplied and subtracted by the same result. So this will be Z into Z minus e raised to I theta divided by Z minus e raised to I theta into Z minus e raised to minus I theta. So if I can simplify this further, I'll get this as Z transform of e raised to I theta raised to n will be equal to Z square minus Z e raised to minus I theta divided by, okay, let me do it later. This is Z into Z minus e raised to minus I theta. Okay, I'll write it down later. I'll just simplify the denominator first. This will be Z into Z, a Z square, and then minus Z e raised to minus I theta, and then minus Z e raised to I theta plus e raised to I theta into e raised to minus I theta will be e raised to 0, which is plus 1. So this will be z into z minus, and we know that e raised to minus I theta is nothing but cos theta minus I sin theta. E raised to minus I theta is nothing but cos theta minus I sin theta divided by, this will be a z square here. I can take a minus z common. I'll be left with e raised to minus I theta plus e raised to plus I theta plus 1. So simplifying this further, this will be z times z minus cos theta plus minus into minus a plus I sin theta. Observe this step here. I have just taken all the real parts and the imaginary parts separately. Z minus cos theta, the real part, and minus into minus a plus I sin theta divided by z square minus z into 2 cos theta plus 1. Why into 2 cos theta? E raised to minus I theta plus e raised to I theta. I have written it as 2 cos theta because we know that e raised to I theta plus e raised to minus I theta is nothing but cos theta plus I sin theta. This is for e raised to I theta plus cos theta minus I sin theta. So whenever I add this result, you can see that plus I sin theta and the minus I sin theta get cancelled, and we will be left with 2 cos theta. That is why I have written this e raised to minus I theta plus e raised to I theta as 2 cos theta. Now let us separate the real and the imaginary parts. That is, this will be equal to z into z minus cos theta divided by the denominator is z square minus 2z cos theta plus 1, the real part, because the denominator is same, I can separate it, plus the imaginary part I times z into sin theta divided by the denominator z square minus 2z cos theta plus 1. So I shall make use of this result here, that is, we have obtained z transform of e raised to I theta raised to n as that result. So let me replace here. I'll get this as z into z minus cos theta. This will be z into z minus cos theta divided by z square minus 2z cos theta plus 1. And then the imaginary part we have plus I z sin theta divided by z square minus 2z cos theta plus 1, which will be equal to z transform of cos n theta plus I z transform of sin n theta. This result, z transform of e raised to I n theta raised to n, whatever I have obtained, I have just replaced here, and then it is equated to the z transform of cos n theta plus I times z transform of sin n theta. And the last step here is to just compare the real and the imaginary parts. So if you can compare the real and the imaginary parts, you can see that z transform of cos n theta, the real part, is given by z into z minus cos theta divided by z square minus 2z cos theta plus 1, and z transform of sin n theta is given by z sin theta divided by z square minus 2z cos theta plus 1. These are the results what we have obtained for z transform of cos n theta and z transform of sin n theta. So in the next class, let us discuss about what can be or what is the z transforms of the hyperbolic functions, that is the cos hyperbolic function and the sine hyperbolic function, what we mean by initial value theorem, the final value theorem, and inverse z transforms, also how to solve the difference equations by making use of the z transforms. Thank you.